Given two integers a and b, compute their sum without using the plus or minus operators. Return the sum of a and b. Example 1, a equals 1 and b equals 2. Their sum is 3. Example 2, a equals -2 and b equals 3. Their sum is 1. Since we are bypassing high-level arithmetic, we must look at how addition works at the hardware layer. Addition there is broken into two simultaneous jobs, calculating a raw, carry-free baseline sum, and collecting the resulting overflow carries. We can mimic this hardware design perfectly using just two basic bitwise logic gates. The first job is finding the baseline sum while completely ignoring carryovers. Look at the columns. Adding matching ones or matching zeros results in 0, while differing bits result in a 1. This exact behavior is the definition of a bitwise XOR operation. XOR acts as our engine for carry-free addition, yielding a baseline of 14. The second job is tracking the overflows. A carry is only generated when both the top and bottom bits are 1s, which we isolate instantly using a bitwise AND operation. However, a carryover doesn't belong in the slot where it was born, it belongs in the next column to the left. We shift our entire AND result left by one position, creating our final carry map. With our baseline sum and our shifted carries established, we simply loop and repeat the process. We pass these two new inputs back into our logic gates. On every single cycle, the carries cascade down the binary line, shifting left and merging with the sum. The moment our carry map drops to absolute 0, there are no more overflows to process. The remaining XOR baseline holds our finalized, exact answer, 16. We translate our hardware intuition into code by setting up a dynamic execution loop. We treat our variable a as the running baseline sum, and variable b as our carry accumulator. Our loop will continuously merge the carries into the baseline until b drops to absolute 0, meaning no more overflows remain. Inside the loop, we must execute our two hardware functions simultaneously. First, we use the XOR operator to find the carry-free baseline sum. In the exact same breath, we use the AND operator combined with a left shift of 1 to calculate our overflow carries. We use temporary variables here so the two calculations don't interfere with each other's inputs mid-flight. With both states engineered, we advance our loop parameters. We overwrite A with our new baseline sum, and overwrite B with our newly shifted carries. The loop instantly primes itself for the next calculation cycle. Here is a crucial cross-platform tip. If you are writing this in Java or C++, standard 32-bit integers handle integer overflows and negative numbers automatically at the hardware layer. But if you are using Python, integers have infinite precision and never overflow. To keep Python from looping infinitely on negative numbers, you must manually apply a bitwise mask of 32 ones to clamp the values down to a standard 32-bit size. As our variables cycle, the carries cascade down the line until they completely run out. The moment b hits 0, the loop breaks cleanly. We exit the block, return our finalized value of a, and our addition is complete. For 32-bit integers, the carry loop runs at most 32 times, and each iteration does constant time bitwise work, so time is O of 1. We only keep a few scalar variables, so extra space is O of 1. Pseudocode for getSum. While b is not 0, compute carry as a bitwise and shifted left, set a to the XOR sum, and move the carry into b. When b reaches 0, return a.